Hello everybody, welcome to my channel. Today we have an amazing problem for you guys, right? So it's called search any 2D matrix, right? So it's a very good problem, man. So let's quickly go ahead and read the problem statement. So we're given a m by n matrix, right? Integer matrix with the following properties, right? Each row is sorted in non-decreasing order, right? So sorted in non-decreasing order. And it also says that the first integer of each row is greater than the last integer of the previous row, right? So far we've been told that all the rows are sorted, right? And non-decreasing, and then the first number of each row is greater than the last number of the previous row. So very good to know. So it says we'll be giving a target, right? And we need to return true if the target is in matrix or false otherwise, right? So, okay, so we must write our solution in log of m times n, right? So very interesting. They put that requirement on us, right? Because we could have easily done this problem, guys, by two for loop, right, to find that respective target, right? So because of that constraint now, the problem is gonna become a little bit harder to do, right? But don't worry, guys, I'm gonna get you guys to the right solution. So not too bad, right? So the brute force solution, right? Doing two for loops, right? We look through every rows, right? And for every row, every column, right, will be a m times n, right? So time complexity, right? So this is not too efficient. They want a log of m times n, right? So we need to do better. So how can we do that? How, right? So log, right, of this, right? So it kind of tells me that we need to kind of apply some kind of boundary search somehow, right, to kind of achieve that time complexity, right? Because I think this is the searches, strategy that we know about, right? That can kind of give us that time complexity that they're asking for. Okay. Should we use additional data structures? Not too sure, so we kind of have to brainstorm, guys. Brainstorming is kind of important. Okay, so how can boundary search be used here? So we got to know a bunch of row 2D matrix. Okay. It's not that straightforward to apply, right? So we kind of have to, because we're not used to that, 2D array, things like that, right? So maybe there's a way we could kind of, put all of this stuff, right? Some kind of a 1D array, right? If we were to get a 1D array, put everything in there, right? Pretty much clone it in a way, right? And then we could apply boundary search over that thing, right? Maybe that could give us the time complexity they're looking for, right? But if we actually create, guys, right, a 1D array, right, pretty much will, so creating 1D array, right, of the elements would give us the elements in sorted order, right? So that's the thing about it, right? That's why I said we would be beneficial if we could convert this into a 1D array. And once we get the elements in a sorted 1D array, right, you know what I'm saying? We could apply boundary search, but that would not be efficient, guys, because we would need to create that 1D array, right? Okay, not only that's additional space, right? Also the time complexity, guys, will still be of m times n, because to create that array it will cost us m times n, guys, because we need to look through every cell, guys, right, to put them in that new 1D array, right? And then apply boundary search, right? So it's still not too efficient, because we need to get that right. So that's out of the question. Okay. We know how to apply one boundary search on a 1D array, right? But can't do it but on this matrix. Maybe what we can do, guys, right? Maybe we could not create the 1D array, right? But kind of, treat the 2D matrix as a 1D array, right? So by treating it as a 1D array, maybe then, guys, we could apply boundary search on it, right? Without having to actually create the 1D array, right? And maybe do some kind of a conversion type of thing to kind of know which row, which matrix, which row, which column a particular element is included in, right? So what we're gonna do, guys, is go to the whiteboard so everything can make sense, right? See how by converting into a 1D array, we can use boundary search to somehow solve this problem, right? So yeah, guys, we'll be going over the walkthrough that I talked about, right? So you guys can kind of see, right, that we have our 2D matrix here, and we have our equivalent 1D matrix, right, in our virtual 1D matrix. Like we said, we're not gonna actually build the 1D matrix, right? Because the time complexity would not be good for that, right? So we're gonna do something else. We're gonna treat this 2D matrix as a 1D matrix, right? This is our flattened 1D array, right? So something that we used to and we know how to apply better research to a one-dimensional array, right? So this is exactly by treating the 2D matrix, right? We can, as a 1D array, we can easily apply pattern research and find the target thing that we're looking for, right? So this is exactly what we're going to be going over, guys, right? So what we're going to have to do, we need to initialize. So we treat, as we're treating it like that, right? I'm just doing this so you guys can visualize it, right? So it kind of makes sense, right? So our initial pointer is going to be a left pointer here, and our right pointer is going to be at the last element, which is the last element here, right? So to the last element in the matrix, right? So that's our initial search space initially, okay? And then now, guys, we're gonna apply better search, right? So index 5 will be our middle element, guys, right? In our 1D matrix that, that we're just, that represents this 2D matrix, right? So hopefully you guys can visualize it, right? So this is for visualization here, right? So as we have our search pair, we see 5 is our index, right? So if we have 5 here, right, we need to kind of now know which number that we're referencing here, right? Which number would have been at index 5, uh, which number, right, would have been at index 5 if we were to create if we were to create the real 1D matrix, right? Which number would that be, right? So we need to do that, right? So to actually get that number, we need to kind of convert that index that we get here, right, into um, matrix coordinates, right, which includes the row, right, and the column, right? So we kind of need those two pieces of information before we know which number that would be, guys, right? Because we're not actually creating the matrix, right? This is what we need to kind of convert it back into our row and column coordinates, get the actual number, and know, should we go left in our thing or in our array, or should we go right, right? So this is what it's important to actually know which number that we're pointing at, right? So this is index 5, right? So which number would have index 5, right? So convert it back into row and column coordinates. So how are we going to do that, right? Would have been your next question. So I'm going to show you guys exactly how to do it. So to get that, guys, right? We could kind of see that the 1D array, right, is kind of partitioned into sections, right? Pretty much into sections of 4, right? Which kind of uh sees that it represents the number of columns that we have, right? And it is that, right? It does represent the number of columns that we have, right? That's why I kind of trying to make it clear for you guys. You see, if we can imagine the 1D matrix array, right, into sections of number of columns, right, we could easily make this thing that I'm about to show you guys kind of intuitive. It kind of makes sense, right? Since we can fit only 4 numbers per row, right, because it's bounded by the number of columns that we have, right? We gonna use some kind of so we know that we see that the first row takes care of the first 4 columns, right? And then the second row takes care of the next 4 column, right? And it's the last row represents the last 4 number, right? So we kind of getting somewhere, right? So what we're gonna have to do, guys, right, is to know which row that particular index belongs to, right? So index 5, right? Which row does it belong to, guys, right? We could visually see it. It belongs to the second row, right? The second set of 4 numbers, right? Which represents the second row, right? So it's easily to do visually, right? But we need some kind of formula, right? So how do we know that, right? So the formula that we're going to use, guys, right, is going to be the index, right? So to get the row that a particular index belongs to, right? We do index divided by the number of columns that we have, right? Because we can only right, fit number of columns per row, right? So we do index divided by columns, right? Okay, index divided by columns gives you, right, for this example, right, we have 5 divided by 4, right, which gives you 1 point something, right? So this is this index, right? And the row, right, that it is in, right? And 2D matrix is actually in row one, right? So we get our row number, right? Right. So it's in the second set of numbers, right? Because we have four rows and the we have four columns, and 0 to 3 takes care of the first set of four, right? Not four numbers, right? And I mean any number after that will be in the next row, or beyond, right? So this is why it's logically makes sense that 11, like it's there. Okay. So what's next for us, right? To get the actual column, guys, right? Column and number belongs to is to do the modulus, guys, right? Do the modulus, okay? And for this example, we see 5 mod uh 1, right? Equals 1. No, 5 mod 4 equals 1, right? So that's kind of the remainder, right? That's what modulus does, right? So we do modulus, guy, right? Because if you kind of think about it a little bit, right? See, so we see that it's partitioned into section, right? We see you had 0, 1, 2, 3, right? And then it restarts again, right? 0, 1, 2, 3, right? But we're not actually doing that, right? It's a 1D matrix, right? It doesn't restart, right? So we need to, it's continuous, right? It's a 0, 1, 2, 3, 4, 5, 6, 7, right? So if we want to get the actual column, right, we need to do the modulus, right? Because it repeats again, right? Because it's everything, it goes from, so the modulus is how the modulus work, guys, right? It gives us the remainder, right? So it generates a number from 0 to 3, guys, right? The modulus, okay? So that's how we easily can index where a particular column is, right? So this is what it does, right? Because it repeats over from 0 to 3, right? So this is how we can easily do that, okay? So hopefully it kind of makes sense, right? So once we get that, guys, we continue our binary search, right? We get our column, which is row, row 1, column 1, okay? Once we do that, we see that 11 is greater than 3, right? The target that we're looking for. So we have to make decisions, right? And we know that we have to go to the left, right? So our search space is here, right? We check so now we do binary search again. We see 5 is the middle element, right? And we see 5 greater than, yeah, 5 is indeed greater, right? So we update that. We go to the left, right? And we're here, guys. We see that no, calculate the midpoint. It's index 0. Then we just check, is 1 greater? No, it's not. So we go to the right, and the left pointer gets updated, right? To bring out the same thing. 3 is the target that we're looking for. We return 3. We return true because we were able to find the target element that they were asking, right? So hopefully it kind of made sense, guys, right? How this all works. So the main gist of this problem is to to uh, flatten the 2D matrix into a 1D matrix, right? And treating it as a 1D array, right? And then get the index, right, of the middle elements, right? Once you get the middle elements, right, convert it back into matrix coordinates, right? So you can get the actual number in that you're referencing, right? And then you see if it equals to target, return true. If not, you make decisions to go left or right, just as if we were doing it like usually, right? So yeah, let's quickly go ahead and code that up real quick. So yeah, guys, hopefully everything made sense. So let's quickly get into the code, guys, right? The code is gonna be relatively simple. Like I said, we're gonna count the number of a matrix, number of rows, right? And then we're gonna get the number of columns. Right? Okay. And then, oh God, we gotta initialize our search space, right? Which is, the left pointer is gonna be index 0, right? And then the right pointer is gonna be pointing at the last element in the matrix, right? Because that's our search space, okay? So it's gonna be done by doing rows, right? Times calls -1, right? Because like I said, we're treating it as a 1D matrix, right? Even though we're not really building that matrix, guys, right? Hopefully the walkthrough made sense. So let me know in the comment section if you guys understood everything I went through. And then we're gonna calculate the middle element, guys, right? Which is done by left standard thing we know by now, right? To avoid integer overflow, we do that. And what's next for us to do, guys, right? The next thing for us to do is to uh, check if the element that we're at, right? Is it that so we're gonna need to do it for better. So it could be better, right? So we need to convert that into we need to get the actual element, right? So remember the conversion that we did in the walkthrough uh, to get the row that the middle element is in, right? So we calculated the midpoint, right? In a virtual in a virtual array, right? 1D array, right? So we need to convert it back into column and call coordinates, right? So we can get the actual element in the 2D matrix, right? So we set that we set that, in which set it belongs to, right? Which row we do mid divided by calls, right? Number of columns, right? And then we see do mid mod the number of columns, right? So once we get that element, right? Hopefully, I did explain it, in that walkthrough, so can imagine it's in sections, right? So once we know the element, so we check once we get the element, right? Could do elements. Number, let's do number instead, right? To make it number. So if the number that we're at right now, the midpoint, right, equals to target, we could easily return true, right? And then we get the case where the number is not equals to the target, right? So we kind of need to know which part we could discard of, because it's kind of sorted in a way, right? So it's sorted actually. So we can use that to our advantage, right? So if the number, right, that we're pointing at right now, right, is it um is it less than the target? If it's less than the target, then we can ignore everything to our left side because everything to our left is going to be smaller, right? It's just standard better search, guys, right? We discard of that, and then once we discard of everything to our left side, we go to the right, right? We also have to worry about the other case where a number is greater, right, than the target. If it's greater than the target, I'm going to ignore everything to my right. I'm going to go to the left, right? And after that, we're good. So if we never end up finding an answer, right, we return false, guys, right? So to recap, we get the number of columns, number of rows and columns, right? And then we define our initial search space, right? Treating the 2D matrix as a 1D matrix. So we're flattening it a bit, right? Kind of imagine that. And then we calculate the midpoint, right? Of that, the midpoint. And we calculate the midpoint by using the formula, right? And then we kind of convert back the midpoint into columns, into a row and column coordinates, right? So we can get the actual number inside of the matrix. And then we check is equal to target if it is true. If it's not, we make decisions to go left or right, okay? Okay, make a little small mistake. Let's press run code. Looks good so far. Press submit. Awesome, guys. We're able to pass all the test cases, guys. So I want to thank you guys for taking the time to kind of watch this video. If you guys found value, make sure to give me a like. If you guys are new here, make sure to subscribe because I'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.